So our final application, our final topic in classical gravitational dynamics is going to be looking at how the Virial Theorem is a useful concept in helping us learn about clusters of galaxies. You know, much, much bigger in scale than the stars that we looked at, but in a way kind of smaller because a star, you know, we talked about it as essentially a big ball of gas where the individual atoms are moving around randomly and producing the thermal energy. The number of atoms is huge. You know, it's much more than Avogadro's number, 10 to the 20, 10 to the 30. I don't know what the number is for number of atoms in a star. In a galaxy cluster, it might just be a few dozen, maybe 100, maybe 1,000 in the largest clusters. So it's much smaller number statistics. So we have to be a little bit more concerned with the statistical, as I say here, ergodicity. You know, if you have very, very large numbers, then you can be clear that basically any subsample that you look at, any time snapshot that you look at, it's going to be representative of everything else, right? The time averages would be the same as ensemble averages. Any time that you choose it will be representative of any other time. But here we have to worry. We only get one snapshot of a galaxy cluster, right? It doesn't change at all on human lifetime scales. So we only get our one chance to look at it. And, you know, yes, we're going to be summing over the n objects that's going to be larger than one. But yeah, so we have to make assumptions about the fact that the statistical averages that we see are actually good statistical averages. So we'll talk about that a little bit. The goal here is actually going to be to use these random motions and random things that we observe for this one snapshot in a galaxy cluster to learn something about the mass of the cluster. You can actually use the Virial Theorem to solve for the mass of the cluster. This is what Zwicky did in the 1930s. We'll talk more about him at the end. But yeah, so we've got our kinetic energy and our total gravitational potential energy that you can compute from the Virial Theorem. Kinetic energy is kind of the easier one. You know, it's just 1/2 mv squared sum. We're going to separate out the mass and the v squared because the mass is going to be the thing we want to solve for. That means that this ensemble average of v squared has to be defined in a way where it's really the same thing as this sum. So the ensemble average v squared is essentially a weighted ratio of sums, similar to what we've talked about before. The numerator is the sum we really want. The denominator is the m total, essentially, so that, you know, so that it turns out to equal the same thing. Well, the simplest thing we could do is that if we don't know the masses of the individual galaxies, then we can't really do this observationally exactly. Well, if you assume that that these little m's are essentially either identical for all the members of the cluster or that they're weighted in the same way, you can sort of simplify this just by sort of taking them out of the sums in the numerator and denominator and just taking the variances of the v squareds that you see. That's one approximate way. You could probably also use other proxies for the masses of the individual galaxies, right? These little m's in the numerator and denominator, because they're in both numerator and denominator, that means they don't have to have the units of kilograms or anything. You could use something that's proportional to the mass, like the brightness, or maybe the size of the galaxy that you can measure in angular units on the sky. But you could try a proxy to do a more proper weighted set of sums rather than just the unweighted one that you can do statistically. The other limiting factor, of course, is that we don't get the full velocity vector for something as distant as a galaxy. Again, it's not going to evolve on human timescales, so we're never going to see proper motions moving transversely across the sky. All we have is the Doppler component that's parallel to our line of sight towards the galaxy. But again, if the galaxy is ergodic and everything is sort of random and even isotropic in space and in momentum space, then you can assume that the one component that we see is representative of the other two components. So the full v squared is just going to be 3 times the v squared of the one component that you can see. That's an assumption, and you can do a little bit better sometimes, and we'll talk about that. But yeah, so that's essentially breaking up the kinetic energy into this m that we eventually want to solve for, and this v squared that you can get from data. The gravitational potential energy we've written before, and you can sort of do a similar thing. You can take out the m squared into an m total squared, and then this 1 over r that you want to get in terms of the units of this quantity, you can define something called the gravitational radius of the entire cluster. That's defined as essentially solving this for 1 over rg. It's just going to be 1 over m total squared times this weighted sum. Again, you need to either have a proxies from luminosity or something for the individual objects, or you can ignore the fact that the different objects have different masses. I guess another way of talking about that is an assumption that the masses in this sum and the distances in this sum, you can assume that they're sampled from two independent distributions, which kind of makes sense. The separations that you see at any one time are just some random realization. If you were to measure this in another billion years, you'd be seeing different separations, but the masses wouldn't change. So you could think about separating this into two sort of statistical things that are multiplied by one another. For example, you could look at just the sum of the MIMJs as you do this double sum over the unique pairs, right? So that would mean that you're doing a sum over n times n minus 1 over 2 unique terms, and that would mean that you would have to define an ensemble averaged m squared. But if you just sort of assume it's a large number, this is just n squared, m squared up here in the numerator, and that's roughly m total squared, right? That's what this ensemble average m squared is. It's sort of the most likely m squared, squared mass of an individual galaxy in the cluster, but multiply that by the number of them in the cluster squared, and you just get the total mass squared. And then you could do a separate part for the distance, right? So you could take this this assumption that we just derived for the mass part of it and plug it in for that piece of it there, right? And then the other part would have to be this ensemble average of the 1 over r, right? The individual relative distances between all the different objects in the cluster. And well, if we've separated them out, you can just take the ensemble average that way, sum over all the unique pairs in the numerator of the 1 over r between those two different things, and then weight that by the sum over, essentially n times n minus 1 over 2. So you could sort of do it that way. And yeah, so if you could actually measure that quantity, you could plug this into one side of the Virial theorem, plug that kinetic energy into the other side, and now we have something where you can solve for the total mass in terms of things that you can statistically measure for a cluster. Yeah, I just did that here, right? It's just essentially a v squared times r, or a 1 over 1 minus r, if that's how you want to do the statistical average. And yeah, you have to take observational limitations into account. You can only measure the VR squared and not the total V magnitude squared. Because, and the 1 over R you can't measure either, right? That's a 3-dimensional distance between different members of the cluster, but all we can see is just one image on the sky. So if all we see are the projected separations, I'll call that 1 over R perpendicular, right? That's just the separations that we see on the canvas of the sky. You can do an average of those. In general, the distance that we see is going to be smaller than the 3D distance between any two galaxies. So there's got to be a correction factor for it. And it was sort of worked out in the 1960s that on average, if everything was distributed isotropically in space, there's this pi over 2 difference between these two different quantities. So you can plug that in. You can plug in this factor of 3 for the velocities and get an observable virial mass estimation, right? The mass of the cluster can be given by these two different directly observable quantities. And this was done, decades and decades ago, and there's been a lot of work to try to provide some specific improvements to how the data are processed to get these specific input quantities, and I'll have a link to some of these papers. Of course, the other option, the other source of error in all this could be that this galaxy cluster is not in virial equilibrium. Remember our collapsing gas cloud or our expanding gas cloud, if the two terms in the virial equation were not exactly balancing one another, if it hadn't yet settled into equilibrium. That might be the case for galaxy clusters too, and there's been a lot of work done to try to determine how that would affect these kinds of mass estimates. So yeah, in the lecture notes, there's about another half a page of discussion of different methods that could be sort of pieced together with this virial mass estimator. The other thing to talk about here is the history. Pre-Zwicky was a very colorful character in astronomy. He of course applied this method. He was one of the first people to apply this method to galaxy clusters, and of course he found that the total mass of the cluster was something like 100 times the mass that you can estimate just by adding up the luminous matter, the stars and glowing gas. If you try to figure out how much mass that stuff takes, it's nothing compared to the mass that's actually there that you can measure from the Virial theorem. So he came up with the idea of dark matter, that is still sticking around to this day. Zwicky was a very, very interesting character, very well respected and very influential, such that there are these survey facilities that still have his name today, like the ZTF there. He was also very contentious. He made many enemies in astronomy. He accused another astronomer of trying to kill him by putting a rattlesnake in his office, and he threatened, to retaliate. And yeah. So it's interesting to look back, almost 100 years with the comfort of distance on characters like this. By the way, also, there in the last couple of years, there have also been studies of the work of Lundmark, who seemed prior to Zwicky to actually have put all the pieces together to do this virial estimation for the masses of clusters, and essentially concluding that there must be dark matter. He even used the same German word, I think, about several years prior to Zwicky's publications. But yeah, for some reason, Lundmark's contributions got sort of forgotten about, but I think in future years we'll see both Lundmark and Zwicky sort of being given credit as co-discoverers of the cluster dark matter. All right, I guess that is it for classical dynamics then, and so next week we will move on to the radiative part of the radiative and dynamical processes course. All right.